Okay, great.
Um, and without further ado, I can see we have a good attendance for the last talk for the year. I just wanted to introduce myself. My name is Oleg, and I will be your co-host, for our last talk for the year today. Um, Susan Webb will assist with the question session in the end of the talk. I wanted to welcome all the SAGA members and everyone who's tuning in for today's talk. And if you're keen to share some of the work that you're doing, you can present it. Please get in touch with me. I'll drop my email in the chat, in the Zoom chat, and I will either organize it or put you in touch with our talks coordinator. I wanted to say a huge thanks to our corporate members, Anglo American, De Beers, SkyTem, Excalibur Airborne, Geofocus, Digital Surveying, with a special note to Digital Surveying, who's also sponsoring our Zoom platform. If you're keen to become a corporate member, SAGA's corporate member, please let us know. You can either use my email or I'll drop an admin email in the chat. Um, just wanted to say that your help and support is greatly appreciated. Today's SAGA talk is presented by Dr. Lynette Kirkpatrick on multidisciplinary geophysics for sustainable future on Namibia's southwestern coast. Dr. Kirkpatrick is a section geophysicist at NAMDAB Diamond Corporation with over 20 years experience in ultra-high resolution marine geosurvey and geophysical data interpretation. She holds a PhD in marine geology and geophysics from UKZN. If you have any questions, please type them in the chat during the talk, because we'll have to go through them at the end of the talk. And just remember, please keep your mics muted and cameras switched off during the talk to avoid distracting the presenter. Lynette, over to you.
Cool. Good afternoon, everyone. Thank you, Oleg, for the introduction. I'll just dive right in. I originally gave this talk 2 months ago, as you can see from the date at the conference. And it was important to me then, as it is now, to sort of contextualize the work I've been doing in recent years into the theme for SAGA this year, which is down here in green at the bottom, collaborative geoscience for critical supply. Okay, so for me, the collaborative part underpins basically everything I and we do at NAMDEB. And I can, I think, easily show you that today, certainly in the sense of integrating geoscience and mining and sustainability disciplines. But then when I was thinking about the critical supply component of the theme, I think the organizer's intent was to explore minerals or things that are critical to keep a system going. So in this global context with post-COVID low demand for diamonds and with diamond indices being at a major, if not all-time low, diamonds themselves would probably not be considered critical supply items. However, I think what I'd like to propose here today, and I did at SAG, is that in the local Namibian context, even if it's only the southwestern Namibian context, but it's not, diamonds are a critical supply item. So people here need diamonds not for their own sake, but because the diamond mining industry is still critical to the livelihoods of the communities of southern Namibia. At the talk at SAGA, I encouraged everyone to take a trip down south to Oranjemund. So wherever you are in southern Africa, a trip to Oranjemund would be a great experience to just experience the multi-generational legacy and the passion that is alive for the diamond industry that is alive and well there. Yeah, so let me see if I can. The slide's a bit laggy. What you will see if you have the privilege of oops, no, it's going back south to Oranjemund, is that NAMDEB, apart from mining diamonds, has the privilege of operating in really one of the most, in my opinion, certainly the most beautiful, maybe desolate, maybe isolated, but certainly pristine coastlines of the world. That's why I've gathered these photos here. It's a responsibility that NAMDEB holds very dear, very dear. And we share this coastline with small local communities, like small-scale fishermen. Please file that away in your memories for later in the talk, because I'll bring it back to them at the end. And so when I think about the word critical in the theme for SAGA, I'm cognizant of the fact that it cannot be exclusively used for either minerals or energy or environment or families or even a country's economy. Okay, so with that long introduction and praise, I want to just bring us back to geophysics, geoscience. Namdeb's onshore and nearshore operation and how we're collaboratively working to keep mining diamonds well into the future, and how we're doing it in the context of our responsibility to the future, to the planet, to innovative science, and actually how we're having a lot of fun and purpose doing it all. So before I get into the actual geophysics, I want to just set the geological context. Many of you are familiar with these slides, especially these two on the right. So Namibia, the west coast of Namibia hosts the world's largest diamond megaplacer, comprising 95% gem quality diamonds by definition. The diamonds have been transported from the interior of South Africa, from some of the richest kimberlites known in the world, via the Orange River system from their source there. And the map shows the catchment area of the Orange River and a single conduit, which has gathered and concentrated the diamonds at one exit point on the coast, over here near the town of Aranyuat. The Orange River delivered them into a marine system. So not only did they get concentrated on their way, but they were delivered into a marine system that is one of the most energetic coastlines in the world. And the sediment that came along with them down the river is diluted, has been continuously diluted, which would dilute it was whittled away, and the marine processes act on the river outfall to concentrate diamonds in a variety of ore bodies, and you can see them illustrated here. So here's the exit point. You've got gravel spits, linear beaches, pocket beaches as you go further north, and deflation deposits, and of course the marine placer offshore lag deposit, which is mined by our sister company, De Beers Marine Namibia. So you can see that the placer covers an enormous area. However, despite hosting the most beautiful and high quality diamonds in the world, it's not easy to mine them profitably because a placer deposit is by its very definition inherently variable, which makes economic resource estimation at a local scale extremely, extremely difficult. And this seismic section here at the top shows you what you're up against. So this green horizon here, which is a patchy ore horizon, and you don't see it everywhere, even though it is dispersed and concentrated in a rugged bedrock footwall, a chloritic schist in the south, or in the mining area. But you can see in the seismic section how difficult it is to pick it up. You can't see what's going on. And then on top of that, to make matters worse, you've got a very thin ore horizon. You've got up to, in some cases, 50, 60 meters of sediment above it, and then that's under seawater as well. So you've got a really challenging target. And that's what's mined down here south near Aranyuat. And then furthermore, or what makes matters even more difficult, is as the mine gets more and more remote from the infrastructure at Aranyuat, which is down here, being confident that you're mining in profitable areas becomes increasingly critical. Okay, so this is our target here. This is where Aranyuat is. So while we know that the diamonds are everywhere, at the scale that mining needs to happen to make the deposit economic is challenging in the current climate. So what we needed to do is to develop a framework for ranking prospects and areas to follow up. So we're looking at that area again in the red. And ranking targets in this sort of geology is different from identifying a discrete body like a kimberlite or a massive sulfide or something. For this diamond placer, you can't ever see the diamonds, obviously, and you very seldom can see the host ore body as well. But what we do know, and we know well, is that the bedrock morphology, which is illustrated by the red line, as I said, controls trap site formation. And that bedrock morphology is controlled by two major factors. There's an old structural control that predates the opening of the South Atlantic, and then paleo shorelines or paleo sea level, which concentrates erosive and abrasive wave energy along specific elevations for thousands of years at a time. So if we can start by quantifying those two elements without drilling or sampling, then we're well on our way to bringing confidence to the resource potential. And that's where I'm going with the geophysics, starting with magnetic tensors. But before I expand on how we're going to use magnetic tensors for this project, as an outline of where I'm going in the red block down here, the geophysics in this presentation has three sections. First of all, I want to show you how we've used the ultra-high resolution gradiometer mag and the magnetic tensors to bring confidence to where we should focus our follow-up, and then how we're going to use remote sensing, so satellite imagery, to develop those targets in a sustainable, holistic framework that takes into account really the magnificent coastline that we're working on. And then in amongst those two methods, how we use ultra-high resolution multi-beam echo sounder for ground truthing both the mag and the remote sensing. And that brings the critical quantified information to the resource development and the mine planning teams. They need that to create a bankable resource and maintain the license to operate, which is an environmental legislative requirement. Okay. So we broadly know what is happening with the diamond movement and entrapment and upgrading, But as I said, at the risk of repeating myself in the context of the extreme inherent variability of the deposit, we really needed the geophysics to push the resolution boundaries and extract all the possible geological information from the signal. So essentially maximize the value of the magnetic survey. And that's where magnetic tensors come in very useful. For the resolution and the information that we are after, a low-level fixed-wing horizontal cryostat squid system, which you see illustrated here. This is from 2021, 2022. And just while I'm here, I just want to refer you to Andre's presentation from SAGA, where he presents some updates in the squid development project. But anyway, this was our first prize. We wanted to measure the gradients directly. And this system has been in development as an R&D project in which De Beers has collaborated with various industry specialists for, I've got in my notes over 10 years, but I think it's closer to 20 years. And Namibia was planning to fly the first production squid survey with the system in early 2023. It was just pending the final testing and the civil aviation approval. But unfortunately, it was not to be. So first, global politics got in the way, with a delay in the final testing phase due to the liquid helium shortage that occurred when the Russia-Ukraine war broke out. And then just before we were due to mobilize, very sadly, there was a low-level survey fatality that put the squid commissioning on hold and brought, in fact, all low-level survey under very close scrutiny from a safety perspective. But it was okay. We proceeded. Time pressed on, and we proceeded with a more traditional mag radiometer survey with NRG. So operationally, we couldn't directly measure tensors, but we know that if the TMI, total magnetic intensity data, is sufficiently high quality and acquisition is at high enough resolution so that there's no aliasing of the TMI grid, we can derive the tensors from the grid of the total magnetic intensity and still get the benefits of the true potential field tensors. So that is credit to the work of Schmidt and Clark, and I think there's a reference somewhere in the presentation later, and that's the original work. And then more recently, Pratt and McKenzie and White from Tensor Research have worked on that practically. So after some discussions on the noise level controls and the thresholds and the survey quality control with NRG, with the project brief being to preserve the high frequency components at all costs. So the point is to keep tight controls on the acquisition data quality so that we don't have to level out the data too vigorously. We don't lose the high frequency component of the signal. We were very happy to go with NRG mag radiometer, survey at 50 meters line spacing, and they gave us a really amazing high quality gradient enhanced data set, which I've got here. So this is a survey area of about 65 kilometers and 5 kilometers onshore and 5 kilometers offshore. So that's the black is the coastline there, which is pretty self-explanatory. But obviously the high quality data was helped sufficiently here by, significantly by the fact that the geology of the area lends itself very well to a magnetic method. Got a nice magnetically quiet basement, so anything different shows up really well. You can get a sense anyway from this how clean the data set is from these two gridded images. On the left is the gradient enhanced TMI, and on the right is the normalized source strength. Normalized source strength concept developed by Clark 2012 based on the work of Wilson, as I've referenced there in 1985, but it's a parameter that can be derived from the eigenvalues. It's very useful because it's semi-independent of the source magnetization direction. So it peaks, it's like an analytical signal, it peaks directly over the anomaly source for discrete bodies and over the edges of narrower targets and along the central axis of elongate targets, which you can see here we've got quite a few of. And yeah, by removing the influence of the magnetization direction, it basically just simplifies the anomaly classification process. And it helps define structural features, constrains local strike directions, and all of that facilitates 3D modeling. And that's really useful for recovering geological attributes of an anomaly. And I want to show you later how we did that with a program called Fast Track. But just to dwell here a little bit longer, at this scale, you can already start to get a sense of the target definitions and sort of regional controls. For example, the TMI shows that we can sort of broadly divide the area into 3 magnetic domains. You've got a southern higher TMI sort of background signature, then you've got a central lower magnetic intensity with this lineament going through it, and then clearly you've got the northern section, which we know is dominated by ultramafics, some smaller intrusive bodies and things. And I'll come back to the normalized source strength a little bit later, but I want to stay here with the TMI and the basic filters a bit longer because it's really such beautiful data. Okay, so now I'm zooming in. You can see the scale there, 4 kilometers. Remember, this is about 5 kilometers offshore the data stretches. We're down in the south of the survey area. You can straight away see a readily developed, you can straight away see that there's a well-developed drainage sort of network onshore, and that's highlighted very well by the tilt derivative. Interestingly, or maybe expectedly, the drainage network is not really readily visible on the satellite imagery or on the ground, covered by a lot of sort of wind-blown sand, but it is very shallow. But this is essentially, therefore, the first time we've seen the extent of the drainage system. And it's of interest because for a placer deposit, a river system is a source of transported material, as I explained at the beginning. But we can see this is a short-headed system. It doesn't stretch inshore, so it's not brought diamonds to the coast. But the material it has brought could either be a trapping mechanism, which would be potentially upgrading, or a diluting mechanism, which would be downgrading, and that would be a prospect ranking criteria. Okay, so then you can see that this sort of magnetic feature that I've just put there in the dotted line somewhat bounds a zone of offshore slightly higher magnetic intensity, and I've put the tilt derivative on that. Go back here. You can see it's sort of characterized by a magnetically active basement. See there's cross-cut by dikes, maybe some drainage features, basement structures. And again, as a very first order observation, we can say that it's complicated. Whether those magnetic features are upgrading or trapping mechanisms or downgrading mechanisms needs to be unraveled with the geological history. But what I am confident of here is that the basement is shallower and downfaulted to the north. That's based on my understanding of the regional geology and mag work we've done in the south in the past. And that is an important ranking criteria. So in combination, then the drainage network introduces a couple of factors that we need to unravel and then take the questions further, like maybe if there's been some interaction of groundwater that could have caused silicification or conglomerates to form offshore. Has the drainage network extended offshore? Could conglomerates lock up diamonds or trap diamonds? And these are just examples of criteria we have to consider, but they are tangible criteria, which we would not have had without the MAG. So that's really valuable. And then I quickly want to contrast the offshore area 2 here to offshore area 3, which is a little bit further north. So it's in that quieter zone north of this lineament. A few dominant magnetic lineates which broadly align north-south, which is the regional signature of the regional basement fabric, which we know is inherited from the closure of the Adamastor Ocean, predates the introduction of diamonds to the coast, but here with very interesting little kinks in them. And then you see this other, you can see my pointer here, this other sort of coast parallel magnetic feature, which is a very interesting magnetic anomaly. And so we have another series of criteria to unravel here, to unravel the significance of, the timing of, and how important are these features in combination with water depth and relative basement depth compared to the south. Okay, so that's just a little bit of unpacking there. So I've showed you a lot of info in the TMI, but because the placer is large and the controls are very, very subtle. So these little offsets and the downfaulting is in the order of, half a meter to a meter. It's very subtle. So I need to map all these features accurately and then try and take the confidence of the geological model up another notch. And that's where the fast track and the multi-track that I was talking about, the tensors and the normalized source strength come in. Okay. So, yes. Here, okay, wait. So today, I'm going to just show you an example of the development of one of the prospects using the tensors. And this was preceded by running the fast track system, which I'll explain now on the entire survey area. Fast track is the interpretation software that was developed by Tensor Research. You can see there, credit to them, and Pratt, McKenzie, and White, as part of the De Beers R&D collaboration for squid development. So it requires the magnetic tensors as inputs. Here you go on the left-hand bottom side, and then upward continued normalized source strength. And you can calculate these from the grid in model vision before you get to this step. And then it derives parameters from the tensors over the center of magnetization, the normalized source strength, based entirely on geophysical theory as a series of numerical calculations on individual survey lines. So looks at peaks and troughs, inflection point locations, curvature point locations, interference, amplitudes, widths, wavelengths of the normalized source strength along each survey line. As I said, it's well described in that paper that I've referenced down there. And from those relationships, numerical relationships, you can get indices or attributes which are developed by Pratt et al. Things like a indice for target style. So is it a pipe, elliptic versus a dike, strike direction, the center of magnetization, apparent magnetic susceptibility, reversals, target edges, all those kind of things. I think there's 70 attributes that are calculated. Okay, so here is an example of the results of the fast track process. As I said, it's this I ran on the entire survey block. It runs through every line and outputs a series of anomalies, so discrete points, which are called equal segments, and each segment has its calculated attributes. And here I've plotted it, and then you can plot it in any way you want, and you can combine them and modulate them by different factors. And here I've just plotted depth below ground because that's probably one of our most important criteria, because we want to try and understand the structural framework of the area. So it's modulated here. So this is depth scale on the left, and it's modulated by depth quality factor, which actually in this instance was all quite similar. So you can't see the size of the symbols. You can't really see the changing size. What you see. So what we've got here is east on the right hand side. That's you can see it's draped on the DTM. You can see the relief of the area. This is, I think, 20 times vertical exaggeration. So it's very flat, in other words, but you can see it's completely flat. This is just measured the water surface, and draped over the DTM is the normalized source strength. And you can see how shallow the features are close to the coastline, which is here, actually approaching basically outcropping at surface, probably by a meter or two of sand, and then dipping offshore the various lineaments that we picked up to about 90 meters below sea level, which is very reasonable results. That's all in the right ballpark. So very happy with that. Okay, so now I could have showed you this slide before the previous one, but I just wanted to give you a sense that we've done it for the entire area. This is the tensors that are calculated before we get into fast track. There's BXX on the top left. There's some nice lineaments and some secondary magnetic lineaments. The tensors act as you well know, as directional filters. And then I selected an area and I reduced the noise threshold, because this one calculated for the entire area. I was quite stringent with the noise threshold, and then you reduce it a bit to try and pick out the subtle anomalies a bit more, but just for a small area so I don't inundate myself with false positives. And then I just clipped it out and showed it with a dynamic range. You can see these beautiful lineaments very well and crisply highlighted. And I've just pointed out this feature, which I like very much, and I think is going to be important. Okay, so see, now I've taken that clipped out area, switched it around. The coastline is flat now. North is to the top left, and plotted the anomalies with susceptibility, apparent susceptibility, as calculated by fast track. And now we've got a target. What can I do with this information? How is this meaningful? So this is where the multi-beam comes in. So multi-beam is just a sound reflection from the seafloor. And there's the coastline. You can see we've got in the white area zero data at all. There's nothing, we have no information. The surf zone is there. It's very difficult to acquire data, and there's lots of factors complicating a geophysical survey there. But we do have some multi-beam. This is about 2-meter XY resolution, so it's not the highest resolution you can get. Kilometer scale there, and it does intersect. Well, the anomalies do intersect, but I'm very interested in this coast parallel one. So I've zoomed in here, taken a cross section through the bathy, which is essentially a seafloor DTM, and plotted it here in profile. And this is what really made me excited, because this area highlighted in blue on the bathy is the actual position of the picked anomaly from fast track. And why that's exciting is because if you're a marine geologist, you care, as I've in the introduction said, about paleo shorelines. Paleo sea level still stands. And a signature of a paleo sea level still stand would be a rapid decrease in topography, followed by a shallow or flat lying area, so a sea cliff and a wave cut platform. And that's essentially the signature you see in the bathy here, which is super exciting. And what happens there is the wave base sits and reworks, and you've got concentration of heavy minerals, all sorts of things, combined with probably some inherited structure or antecedent structure that can give a magnetic anomaly. So this was really great to see. And when you take it to this feature here in the near shore, which is also somewhat coast parallel, where we have no data, it lends a lot of confidence because we can't mine this area without mining this area first. The mining methodology moves from onshore to offshore. So we have to tackle this area where we have no data first, and at least we have a sense that there's been things going on that will have helped our prospect upgrading. So there we go. All right. Okay, so we, as the exploration department, are doing everything we can to secure a resource for the future. But that cannot come at the cost of an integrated coastal system, which, as I said, is talking to biodiversity as well as community impacts. And there is decades of work that has gone into understanding sediment movement along the coast. And this sketch here on the right from Spagliari, 2006, is the acceptive model of sediment transport. So we've got material coming in the Orange River. Namdeb mines this area here, and there's a net longshore drift which moves sediment northwards. The idea as well is that it's fractionated. The material that arrives at the coast is fractionated. The coarse gravel fraction remains relatively close to the coastline, making its way slowly northwards within a sort of a narrow distance, essentially probably the surf zone or where the wave base is active and powerful enough to entrain the coarse material. And then the sand fraction has a little bit further, a little bit, it's a little bit lighter. It can move further. It moves offshore and northwards as well. And then the mudded salt fraction dispersed further offshore, southwards, westwards, in suspension generally. And Namdeb's mining philosophy actually relies on this retention of coarse material. So the diamonds would be here in this coarse material. And the way Namdeb mines, as you can see here, that's the processing plant. They strip the overburden, the sand off to expose the bedrock, which is where the diamonds are trapped, and then put the sand onto the beach, either by conveyor or by articulated dump trucks. And then the sea takes that sand and redistributes it northwards, essentially building new beach, pushing the shoreline westwards, and opening up new ground for Namdeb to mine with conventional on-land methods. So we've been doing that for years. It's proven, the philosophy is proven, it's successful. Our entire mine plan relies on that philosophy. However, there's still and remains a long-held perception among the fishing community that the material that Namdeb mines down here and dumps onto the beach travels northwards and smothers rock lobster fishing habitats, which rely on exposed rocky reefs. Maybe something like this, more like this. The coastline was more exposed, less sandy, more exposed rocky reefs, more beautiful rock pools and stuff. And there's long been a dispute amongst the community that that the decline in catches is related to Namdeb's mining operation. So although practical evidence from mining is valid, we were challenged by our Marine Scientific Advisory Committee, which is a completely independent board of scientists that advise Namdeb on coastal management biannually. They suggested we try and gather more data, in particular, recently harness the major advances in the high-resolution seafloor geophysics, as well as the more readily available, freely available, higher resolution remote sensing or satellite imagery, and start putting together a robust data set that give an unbiased assessment on what's happening on the coastline and better contextualize Namdeb operations in the broader ocean climate system. And this has led to some very interesting results. Just opened our eyes again to the beauty and the complexity and literally awe-inspiring natural system that we're functioning within. So the beauty of this data, satellite imagery, is how visual it is. That's very useful when you're collaborating with people from different disciplines and backgrounds and levels of education. A picture definitely tells 1,000 words, there's no doubt. And the bonus here, I think I'm going to show you now, is that the picture translates into some robust scientific data. So here's a picture of the NASA NOAA satellite, from the NASA NOAA Polar Satellite, July 2023. And it shows the magnitude scale of the dust that's blown into the ocean from the Namib Sand Sea, the Namib Desert. It's enormous. And then here's one from slightly furthest focused on the south. It's from 2019. And if you click on the links on the comments here, there's the comments around when you think of dust in the ocean or sand in the ocean, the first thing you think of is the Sahara Desert. but that's obviously one of the world's major sources of dust. But in Southern Africa, we experience major dust storms too, like this one that you can see here. And if you've lived in Oranjemund, you know how significant it is. But I don't think any of us talked about it in the context of where that sand ends up, which is in the ocean. So despite experiencing it in the town for as long as the town has been around, we haven't really, haven't tried to quantify it. So I actually just show you these images to illustrate that we're operating in a larger system. And I know it's all very well to illustrate systems like this at a country and continent scale, but if you're a community of fishermen, you're concerned with putting food on your table and on your family's table and making an income from your local fishing grounds. So the next thing to do was to try and quantify local sediment transport from satellite imagery. And I'll explain how we attempted to do that next. But these two images, which come from the Sentinel-2 satellite, show the scale of sediment input by the Orange River. So you can see the scale there, 1 kilometer. So I'd say in the region of 5 kilometers on this day, you see material suspended from the Orange River. And it reaches a few kilometers offshore. Yeah, you can see it dispersing northward as well. Elevated nearshore turbidity is essentially what you're looking at. And you can see that same in the mining area, just a different change of scale here. We are 200 meters. And I put in some arrows, which I'll talk about again at the end of the presentation or towards the end, which show clear turbidity reflecting ocean currents and dynamics. In this case, it would be rip currents, which circulate water in the near shore. They keep it coming back. I think anyone who's holidaying in Cape Town in the summer will know or may know that the NSRI models this for rip current prediction on all the blue flag beaches. So it's an established and well understood system here of sediment transport and ocean currents. So, all right, so how do you quantify local sediment transport from satellite imagery? I'll give credit to Dr. Leslie Gibson, who's a remote sensing specialist here in Cape Town, and she just identified for us this index, a normalized difference turbidity index, which is used for measuring. It's a relative index, used for measuring water turbidity, commonly used often for estuaries and in freshwater environments as well. But it exploits the scattering and absorption properties of the visible spectrum. In particular, you can see there from the calculation or the formula, the red and green bands. And you can see I've put there the notes. They have different absorption characters and scattering characters when the water has got different sediment load. And clear is -1 and more turbid is 1. So you can calculate that. So what we're looking at here on the GIF here, you can actually just calculate that in the Copernicus browser, which is where you get the Sentinel-2 data. And it's a straightforward band calculation that you do online, and it calculates the NDTI for the scene that you're interested in. But and it's a really good visual way. You can make a little GIF like I showed now, and you can show that to people, which is a really nice way of showing them, giving them a sense of the scale of what's happening here. But if you're at Namibia and your network is a bit slow and your computers are a bit slow, no offense to the Namibia colleagues, you all know what I'm talking about. It's a time-consuming thing to do to try and calculate NDTI and then put it onto your computer and then show people in a presentation or an ArcGIS or something. So it was quite straightforward to develop a code or write a code that can calculate this in Google Earth Engine, which is a platform where all satellite image that's free is available. And then it puts it into a spreadsheet so you don't have to download the images, and then you can do all your stats on that in Excel on a very small data size. So we compiled NDTI values for the 5 years that the Sentinel-2 has been in operation, so since 2018, essentially 2019. And while we're cognizant of the fact that that's not a large data set, it's still 61 months worth of data points, which must allow for some sort of comparisons to be made, and maybe at the start of identifying trends, or at least be the start of building a database. So we took we chose some polygons of interest, one at the Orange River mouth, then we've got 3 in the mining area directly. This multi-beam site is where I have my monitoring site for multi-beam echo sounder, and then that's 50 kilometers from the Orange River mouth. And then we've got other environmental monitoring sites which we keep track of, and then right up to the north, over 200 kilometers north of the Orange River, where have a protection zone where there's no rock lobster fishing or mining, and that's where the sanctuary is, where they can grow and be safe. So it should be a pristine environment. Okay, so you take that, you've got a whole lot of data, and this is where anyone who's good at stats will come in. And a couple of these things were quite new to me this year, but a Schuett chart is a chart that's usually used in quality control processes for monitoring system performances over time. So it plots a time series data within defined control points, which are related to standard deviation, and then helps identify anomalous or abnormal data points. So you can choose a data point and say what was happening on that date, go back to your data set and say, oh, the Orange River was in flood, or we had a big dust storm. And that's what we're using this data for. So we can start figuring out what causes what. It's a means of ground truthing. We can go back to the river flow data, although we don't have a complete record for the Orange River mouth, but we do have further upstream weather data as well. And that will lend a lot of confidence to the actual the data points we've got here, sort of a ground truthing mechanism. And then, but what was also interesting from this data set, so it's good for identifying and finding out the source of anomalies. But what you started seeing here, and this is it's incorrectly labeled, that should be the exclusion zone. This is the pristine area far from the mining activities, is a hint of cyclicity or seasonality, certainly my interpretation, showing that turbidity changes on an annual basis. If you go down here to the two-plant monitoring site, which is where I collect all my multi-beam 50 kilometers for Orange River mouth, you see the same sort of cyclicity. And that talks to something that is bigger than these two sites influencing the turbidity in the area. So that's all we can say about it. If you look at the Orange River mouth here, there's you could maybe squiggly draw some lines to connect some dots here, but it's not so clear. But then if you're in the mining area, the three-plant conveyor, which I showed you the picture of, there's virtually no pattern at all. It's completely randomly dispersed, which is exactly what I want to see. Like that tells me that there's an impact here, and perhaps there's not such an impact at these other sites, or something else is controlling them. Another way of looking at the data is just to look at the total mean NDTI for each site over the 5 years. And you can see, as expected, Orange River, really turbid, much higher turbidity. And as you move northwards, a decreasing turbidity at a mean level. These three sites at the bottom are within the mining area directly. And they are, which would intuitively, also, and they're not only in the mining area, they're also closest to the Orange River mouth, and they are higher turbidity. And then we sort of reach a steady state here. All of these sites are monitoring sites outside of the mining area, and then it declines even more in the rock lobster exclusion zone. Another way of looking at it is Pearson's correlation coefficient, which tells you if any locations are significantly correlated. Interesting, the Orange River is not statistically correlated to anywhere. It's just its own place. And these three sites, which are, if you look on this axis, are northern sites, are not correlated to the southern sites, which is a good thing if you're looking for impact of the mine. Another way of looking at it is looking at monthly averages. Again, you see high turbidity at the Orange River mouth, which is what you expect. You see higher turbidity and not much variation on an annual basis at the sites that are closest to the Orange River mouth and within the mining area. And then you see this hint of cyclicity or seasonality again in the data points that are far from the Orange River and out of the mining area. Okay, so that's some relative numbers and stats. How do we ground truth that? And that brings me back to multi-beam. Okay, so first of all, sediment transport. So I showed just now satellite image with this rip currents development. And this rip currents circulate water and sediment in a nearshore cycle. They retain it in a sort of 300-meter distance from the coastline. And this multi-beam echo signer, so this is our high-resolution multi-beam. It's a 25 centimeter X and Y, so like a pizza box resolution. Basically, you're looking at a pizza box of 2 to 3 centimeters in Z. And this is a seafloor texture that is directly collaborated or directly linked to rip current development. So the swash direction of the waves is in this red arrow, and you see these ridges. And this is about 100 meters here, but we've got about 200 meters before we get to the coastline where we still can't get data because it's too dangerous. So this is a rip current seafloor texture. So that's telling me that what you see in the turbidity does relate to what you see on the sea floor. Obviously, the whole system is dynamic and changing from day to day. So it's lucky that we got this site we get data from twice a year since 2019. So we don't see this texture every single time we acquire data, but we do see it here, which tells us that at this time there was rip currents developed here. Okay. Okay, so now this is the second last slide. Nice to hypothesize things. It's nice to see the evidence on the seafloor of things we observe in the turbidity. Does it relate to sediment movement, though? We also have to note this law of geography or common sense that correlation doesn't actually equal causation. So we bear that in mind. But multi-beam can measure and quantify sediment movement. It's extremely high resolution, although it's very difficult to acquire, and we can only get it when the weather is right, certain conditions, and if you're operating out of the Orange River mouth down here and trying to survey up here, you've got a long transit time as well. So it's difficult. But we have this site where we collect it twice a year, and it's a control site. So the first thing I do with it is classify, use a benthic terrain classification little algorithm, which basically just looks at the change in the elevation at a pixel distance, and you can classify it as sandy seafloor, which is blue, or rocky reef, which is pink, and then I can calculate the square meters and put it in a database and keep an eye on whether the reef is expanding or contracting. And it has been constant since 2019 until April 2023. It has remained virtually identical. I have hardly seen a millimeter change of seafloor classification or terrain. And then in the end of 2023 and early 2024, for the first time, we see encroachment of sandy seafloor onto the rocky reef, and you can see that in profile here. It's quite a lot, actually. And this corresponds to a northward movement of stripping in the mine. Not to say it's causation, but it is a hint or something to unravel, to put into our back of our minds that perhaps we're seeing the limit of the distance of the mining impact on the coasts. So when mining was 20 kilometers away from the site, there was no change at all. And as it moved to about 15 kilometers from the site, we start seeing some sediment encroachment. So that number, 15 kilometers, may be a very important number, and we'll keep checking on that. And if we can quantify distance of transport from the input, that is something to talk about and something to share with stakeholders and something to database and keep track of. Okay, so rounding it all off, taking very long, I brought you through the story from detailed targeting strategy, using magnetic tensors, bringing confidence with the multi-beam on those magnetic features, and then it's all hopes of resource development lose their sparkle if people's livelihoods are put at risk, or if habitat or biodiversity loss is irreversible. So try to use an innovative approach to remote sensing, which will be developed, but it seems to show that turbidity, which is a proxy for sediment in the system, is controlled by a regional seasonal cycle. And in that context, and the existing understanding of longshore drift, multi-beam has quantified the impact distance potentially from the point of sediment input on the coast. And that's critical information that we can feed into the EMPR development plan, the application and renewal of licenses when that becomes important, and communication with community partners and stakeholders. So the aim, final word, is that as we continue to collaborate and use geophysics and all of science to understand the Earth system better, everyone can benefit. Thank you. That's very long.